Okay. So as I was saying, we were dealing with one parameter subgroups. So you have a bunch of group elements which are labeled by this parameter sigma. So A sigma A tau is equal to A sigma plus tau is the equation for one parameter subgroups, which of course immediately tells you that A0 has to be identity and A sigma inverse has to be A minus sigma. And this sigma is a real parameter, could range over the entire real line or some interval over the real line which contains zero, definitely. And if you think of the group G here, this and on this group, as sigma changes, you move along the curve. Of course, you will always go through the origin. Now, this is not unique. There are many, many possibilities. So this could be one parameter subgroup. This could be an entirely different one parameter subgroup. This could be another one, but all of these would, of course, go through the origin. And also, as we said, since we have the group as a manifold, which means every element of the group can be characterized by coordinates, small r coordinates. So basically, a point A sigma can also be thought of as a point in this small r dimensional real space where with coordinates alpha 1 sigma, alpha 2 sigma, and so on. So the job that we undertook in the last class was basically to figure out what kind of equation alpha j sigma would obey. And we started with the statement that this statement, A of sigma plus tau, is A sigma times A tau, translates to alpha j, which are functions of the parameter now. So if you give alpha j the argument sigma plus tau, what you get is the coordinate of this product, and we know how to get coordinates of products by applying the function f. So if you take alpha sigma, the coordinates of the point A sigma, and alpha tau, and give them as arguments to fj, you're going to get this. Of course, you also work the other way around. Replacing tau j. Okay. When I came back again, I think that I tried to put in my MAC address now. Uh, am I still connected?
Yes, sir.
It looks like I am. Okay. And by the way, since you already unmute, keep yourself unmuted, but it would be nice if you were to sort of say yes or no from time to time, even if it was not necessary, because I would need to know whether I'm still actually connected to this. Okay, so the equation that we talked about was, if here you put tau equal to delta sigma, you would
So you're not
end up
audible.
with this equation. You can't hear me at all, or
We lost you in the middle when you were explaining just now. Again, if you were speaking something like 15 seconds ago, you weren't audible.
okay, fine. I don't know whether they may be trying to adjust my network parameters, and that might be causing problems. Let's see. Is this okay? This equation
Yes, sir.
where TKs are nothing but d alpha j sigma d sigma at sigma equal to 0. So basically, if you think of a one parameter subgroup in terms of the coordinates, basically as sigma changes, to essentially have a curve on the smaller dimensional manifold, and the TKs are nothing but the tangents slopes to this curve. So these numbers T1, T2, TR gives you the tangent to this particular one parameter subgroup that you're looking at least the coordinate version of that at the origin. Okay, so this is what TK gives you, and basically what this TK and using this differential equation or rather able to find out alpha j sigma in particular, and of course you also need the initial condition, but that's simple. Alpha j 0 is 0. So starting with this initial condition and this differential equation, for a given t, that is for a given bunch of r real numbers t1, t2, tr, you should be able to get an alpha j sigma. As sigma changes, you change your t to something else. Maybe you change your t to this. Then you are going to get another curve which is tangent to this line at the origin again. Change the t to something else. You're going to get another curve like this, whose tangent here is this red line, red vector. And each of these are different one parameter subgroups. Each basically differentiated from each other by the tangent at the origin. Okay?
Sir,
Yeah.
this tangent vector is in the Rn space, right? Like it's
R-
a normal
R-
curve,
R-
tangent to a curve,
this space.
basically.
Yeah. Of course, you
Ah.
can. Frankly, these are you actually have tangent vectors to your original curves on the.
Sir, you got muted out. Can you just repeat that?
I'm saying that if you look at the group itself, you
Yes.
have curves on the group, right? And the tangent there are tangents to the curves on the group. These tangent vectors, the ones which are given by this bunch of numbers, is nothing but something which represents the tangent vector to the curve out here. Okay, the tangent vector to the group here will plane of the group G at E. These are nothing but a real valued components of the graph once you use this coordinate system. Remember, vectors are components which depend on the coordinate system bias. So when you are using these R numbers, you are basically talking about the components of the actual tangent vector to the curve on the group in terms of this particular coordinate system.
So these are just the tangent vector components.
Yeah, these are these things T1, T2, TR are tangent vector components. Okay?
Okay, sir.
So in fact, there will be this abstract element T that we will often talk about. This T is the tangent to the group G, or to this particular curve on the group G, whose representation using this particular coordinate system that we are using is given by this bunch of R numbers. There's nothing special about group theoretical about this. Whenever you use tangent to a curve on a manifold, you are basically talking about an object which resides, if not on the manifold itself, at least in the tangent plane of the manifold. But when you describe it in a coordinate system, you describe it using components. These numbers are the components. They essentially talk about the tangent vector itself. Okay? But since we are using a particular coordinate system, The tangent vector comes to us in terms of the components T1, T2, Tr, and this is the differential equation that you have. Is that clear?
Yes, sir.
Okay. Now, as we said, we essentially what we can do is ensure that if you have a point somewhere here, some point, specific point, let's say A0 here, or let's call it just A, in the neighborhood of the origin, and that is represented by a specific set of points alpha j. Here I'm putting alpha j without a sigma, basically because I'm talking of the coordinates of a particular point. I should be actually able to find some one parameter subgroup which passes through alpha j. Is that okay? That this can always be done essentially boils down from the fact that here you are getting alpha j sigma tangent, and the relationship between alpha j's and the tangent vectors can be inverted, and you can find out the tangents from the alpha j's. So basically what you're
We can't hear you, sir.
saying is something like this. Always ensure you can hear me again, right?
Yes, now we can.
Okay. This is also important.
Again, we cannot hear you.
Channels of T, that is strange. Why is there's no other, you can see my screen and everything, right? Correct?
No, sir. When you are disconnected, like for a short while, you cannot even see the changes you are making. Once you are connected again, you can see the changes directly.
So that low. Okay, let's hope that they are going to change this by the next day. They're saying that they will incorporate max numbers in their system so that things will work fine. Hopefully, let's see. And this is better than what it was a while ago, right? That is the first time we tried.
Yes.
It's definitely better than that. Okay, what we were saying is something like this. This alpha j actually depends on sigma and t. So it looks like it depends on r plus 1 parameters, r plus 1 arguments. But we also argued that from the differential equation itself, that this actually should depend only on this. That is sigma times t. Of course, this means it depends on sigma t1, sigma t2, up to sigma tr. Not on sigma separately, independently, but sigma in this particular form. So you actually have only real arguments really. And from the equations which Kaiji has obeyed, we argue that we should always be possible, given a point A in the neighborhood of the identity with coordinates alpha j, we should always be able to get a situation like this. Alpha j will be chi j of t. In other words, you will be able to find that one parameter subgroup which actually goes through the point alpha j when sigma is equal to 1. Remember, sorry, this j position is wrong. The j should also be upstairs. Remember, our alpha j sigma t is chi j of sigma times t. So alpha j equals chi j t essentially means that when sigma is 1, my one parameter subgroup goes through this particular point in coordinate space, or in here it goes to the point A when sigma is 1. Is that okay? In
Yes,
other
sir.
words, I should always be able, given alpha j, at least given alpha j in the neighborhood of the origin, I should be able to find out T1, T2, Tr such that alpha j will obey this, or that means Tj can be written down as some function, okay, not xi, I've already used xi, zeta j of alpha. So if you give me alpha 1, alpha 2, alpha r, I should be able to find out T1, T2, Tr, which ensures that the one parameter subgroup which has T1, T2, Tr as the origin, as a tangent at the origin, will actually go through alpha 1, alpha 2, alpha r at sigma equal to 1. So now, this is where we are going to make a big announcement.
Sir,
That is, yeah, tell me.
alpha j sigma equals 1 is basically the mapping of A.
Uh, so here I'm looking at a specific point. I'm calling this
Oh,
A now, not A of sigma. I'm looking at a particular point A. Okay. So A mapped to alpha 1, alpha 2, alpha r.
yes.
Those are coordinates. And I'm saying that my one parameter subgroup, which is really a curve on G, can also be sort of indicated by a curve on this R dimensional real space. And that curve goes to alpha j when sigma is 1. And my original one parameter subgroup goes to A when sigma is 1.
Okay, so
Okay.
that's our choice that sigma is equal to 1.
Yeah, sigma is equal to 1 is our choice right now. But it will also tell you something else. Suppose, and that is important, let me draw this again a bit bigger. Let's say this is my origin identity, and this is the point A. And I have found a particular specific one parameter subgroup, which has a tangent T here, okay, which goes to the point A when sigma is 1. Okay. Now, of course, the one parameter subgroup has elements which depend on the value of sigma. Let's say for some other sigma, let's say sigma equal to half. It goes to this point. Okay. Right? But remember, the coordinates actually depend on this product sigma t. Right? Okay. So if instead of starting with this tangent t, if I started with t by 2 as tangent, then I would get another one parameter subgroup which essentially will follow the same set of elements. But at sigma equal to 1, that will end up here. You get this? Is that okay?
Yes, sir.
In particular, instead of t by 2, if I say, if I start with a one parameter subgroup whose tangent vector is not t but sigma t, where sigma, remember, is a real number, so sigma t is a vector in the same direction, you get a curve which again traces out the same points, but at sigma equal to 1 will be at the point a sigma. Clear? What I was calling a sigma before, the point where I would reach when the parameter is sigma, if I reached a when the parameter is 1, I would reach a of sigma. Of course, a here is a of 1. I would reach a of sigma at sigma of 1 if instead of starting with this OPS, I started with a different OPS with a tangent vector which is sigma times bigger or smaller, depending on the value of sigma. Is that clear? Now, notation, which is, I'm going to say this thing, that chi j of t is equal to alpha j, which we said is equivalent to tj's, the tangent vector components becoming zeta j's of alpha. That is, these two are essentially the same thing. I will introduce a notation for this. I will say A, this point, which this particular one parameter subgroup reaches when sigma is 1. I will denote this. This is formal at this stage, purely a formal notation. by a notation which should be pretty familiar to all of you. I will call it exp of t. Okay, that's just a name right now. That this exp has properties which are very similar to the exponential function, and in fact, we will call this the exponential function, will become clearer as we go ahead. Do you understand what we are saying? We are saying that if I start with a tangent t, then the point that I reach where sigma is 1 is the point I will call exp. Okay? Clear?
Yes.
This is not a statement about the group element coordinates. It's a statement about the group element itself. I'm calling the group element A, which I reach when sigma is 1, starting with tangent vector t, as exp. But now, can anybody tell me what will this A of sigma be in the same notation? A of sigma is a point which I reach in this particular OPS, starting with the tangent vector t, when the parameter sigma is sigma. Okay. But I will also reach the same point when sigma is 1 if instead of starting with the tangent vector t, I started with the tangent vector sigma. Is that okay? Is this point clear? If instead of starting with tangent vector t, I started with the tangent vector sigma t, I'm essentially saying that I'm going to change the speed by with which I traverse this curve by a factor sigma. So at sigma equal to 1, for this curve, I'm going to reach a sigma. Does that make sense?
Yes.
So if you will now subscribe to this notation, that if I start with the tangent vector t to an OPS, whichever point I reach when sigma reaches 1 is going to be expt. Then what will my notation for a sigma be in the same notation?
PXP sigma t.
Right? Because I will have to start with tangent vector sigma t to get to this point, right? At sigma equal to 1. But now we'll see why this notation is nice. At least partly. If I take exp sigma t, which is basically a of sigma, and multiplied by exp of tau t, what do I get? Exp of sigma t is nothing but a of sigma, right? This is a of tau. And what am I supposed to get? A of sigma plus tau.
A sigma plus tau. Sorry.
But this is exp of
So we cannot hear you.
this aspect of. Okay, what I was saying is that this particular aspect of the exponential function, exp of sigma t times exp of tau t, is exp of sigma plus tau into t. That works fine because this is nothing but a of sigma into a of tau is a of sigma plus tau. This additive part of this argument has translated to the multiplication rule for exponents. So that fact that I'm calling this a equal to exp of t exponent working out. Is that okay?
Yes, sir.
So at least
Sir, are you saying something?
I am saying something and seems like my Can you hear me now?
Yes, now we can hear you.
Yes, sir, but we keep on losing them.
That seems pretty strange. That didn't happen before. What I'm saying is, at a formal level, a basic defining property of exponential, at least the familiar property of exponentials for real functions, that actually works nicely at this stage, right? You have this property. Okay, now, so, okay, so basically what we are saying is we will essentially talk about another way of talking about a group element, which is if you have a group element A which is near the origin, I will think of how to start from the origin along a one parameter subgroup and reach A. And whatever tangent vector allows us to do that when sigma is 1, I will say A is exponential of that tangent vector. But now you realize one thing. For every such tangent vector, there is a unique A.
Sir, if you're saying
Right?
something, not hear you.
Of-
All we heard was for every such tangent vector, there is a
So
unique.
for every such tangent vector, you have a one parameter subgroup starting from the origin, right? So in other, you change the tangent vector to something else, you have another one parameter subgroup curve, right? And so every tangent vector gives you a point A through this exponentiation. And on the other hand, if you give me the point A, I should be able to find the unique one parameter subgroup which passes through A at t at sigma equal to 1. So I should be able to identify T uniquely. Or you could hear me, right?
You went mute for a while.
Correctly. Anyway, let's see. What all I was saying is there are infinitely many different tangent vectors you can pick at the identity. Of course, there could be tangent vectors in different directions as well as tangent vectors in the same direction but different lengths. Choosing different tangent vectors would give you different OPSs, and therefore it would give you different points A. For a given T, there will be only one point A which is going to qualify as EXPT. Conversely, given some point, let's say this point A prime, I should be able to find that one OPS which goes through A prime at sigma equal to 1. And the tangent to that particular curve should be my T prime, which helps me identify A prime as XPT prime. So all I'm saying is there's a one-to-one correspondence. Give me an A, I will be able to find the T. Do you agree with that?
Yes.
And given a T, I should be able to find the T. So you should realize that I can actually, and how many numbers characterize T? Just the components, right? R numbers. So instead of using alpha 1, alpha 2, instead of using these numbers to characterize A, instead of saying that A actually is characterized by these R coordinates, we could just as well say that, okay, how do I identify A? Give me T1, T2, TR, and I've got your um, I've got your got your point A, right? What are coordinates after all? Coordinates are things which, given those numbers, I can identify the element, and given the element, I can identify the numbers. So all I'm saying is, instead of using the original bunch of coordinates alpha 1, alpha 2, alpha r, just as well use these components of the tangent vector to the OPS, which will reach the point A at sigma equal to 1, and call that T1, T2, Tr coordinates for the point A. Is that clear?
Yes, sir.
So this is a new choice of coordinates. So instead of the original alpha, you're using alpha bar, which is basically T1, alpha bar 2, which is T2, and so on. So I've gone from alpha to alpha bar. Change of coordinates, nothing else. And this kind of coordinates, where essentially use the components of the tangent vector to the OPS at the origin to stand for a point where the OPS reaches at sigma equal to 1. You give this a special name. This is a very important bunch of coordinates. You call them canonical coordinates of the first, at least the second kind. Otherwise, you would not have used the word of the first. About those. To us, this is going to be very important, especially because this particular equation actually becomes very, very simple in canonical coordinates for the first kind. Notice that in these canonical coordinates of the first kind, what
Sorry,
are
you're
the
inaudible.
coordinates of this point A sigma? Okay, I'm back, I guess. So if you are talking of a particular OPS which reaches the point A, okay, let me just use this one, reaches the point A. This A1 is T, meaning T1, T2, Tr. What would the coordinates for this point be?
Sigma T1, sigma T.
Sigma T1 bar R at sigma at sigma will be nothing sigma T, right? Sorry, not oops. Set of equations, use of coordinates. The combination rule that would use of functions. So instead of f, I should use f bar. Instead of eta, I should use eta bar. Instead of xi, I should use xi bar, and so on. Changed coordinates would change all these functions. But the J is true in general. Alpha bar J sigma is sigma J. This coordinates of the point at sigma equal to 1, the coordinates of all the other points are just basically scale factors of that. But now, no. notice that the equation that we have will sorry, right? This is nothing but the old equation that we wrote down. D alpha d sigma equals theta jk of alpha sigma times T. For this, now I was really on.
Yes, sir.
So everybody saw this equation at least. Realize that this is nothing but the equation that we had in general for any general coordinate system that we use on the group. We had this equation that for a one parameter subgroup, d alpha d sigma will be eta jk tk. Now that will also happen here. The alpha bar j d sigma will be eta bar jk alpha bar sigma tk, right?
So your screen is stuck.
Screen is stuck. Can you see my cursor moving on the screen now or this line?
Yes. Yes. Now we can see.
The screen was not stuck. I was not doing anything. So I was not changing.
Sir,
Not drawing already. Go ahead.
what is eta bar? Like,
Okay,
what
all I
does the
was
bar
saying is
signify for eta?
the bar signifies I've changed my coordinates from alpha to alpha bar, right?
Yes.
Now the coordinates can always be changed, but if you change them, there's a function f which says how alpha and beta gets combined to give you the combination. That will also change to f bar of alpha bar beta bar, right?
Oh, so it's the function in the new coordinates, basically.
Yeah, the eta bar is also the function. Eta bar is nothing but eta bar jk is del f bar j whatever blah 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 whatever that was del beta bar k and so on and beta bar equal to 0. It's just the same kind of functions but in the new coordinate system. So that equation that we derived did not specify which we have some coordinate system. In will look like. This would of course look the same, right? It's just that you will have to use it. Any confusion about this? But if there are no, am I still connected or
You are connected.
okay? Now I'm getting a bit paranoid. Okay. Okay, but now in this
Cannot hear you properly.
particular coordinate system, the kind this so I just lost connection. So in a more severe way than before. Hopefully by the next day when they put my MAC address in, this should really not be a problem. But anyway, you can see my screen again, right?
Yes, sir.
Now, what is this going to be? You think? D alpha bar G sigma? Yes?
It will just be TJ.
It can be TJ. But TJs, remember, are nothing but the alpha J's. Not alpha J, but alpha J in general. Right? Or for a general, even a general point, you look at alpha bar sigma, you just but so what is alpha? Alpha bar J of sigma. Or this may not look very simple right now because there are too many bars and indices. But as a matrix equation, this becomes very simple. And we will, since now, from now on, we are going to use canonical coordinates of the first kind. Let's say we have to just drop the bars. Then the equation simply becomes alpha equal to eta of alpha times alpha. But this eta, okay, not eta, I should not say eta of alpha. I should say matrix wise is capital H of alpha times alpha. Right? Because this looks like alpha, the bunch of R numbers is an eigenvector of H alpha with eigenvalue 1. But this, of course, can be a way more complicated equation than an eigenvalue equation because H's are maybe complicated functions of alpha. So this is a constant matrix whose eigenvector you're finding out because the matrix itself depends on the eigenvectors. It's a bunch of coupled nonlinear equations, but a much simpler bunch of coupled nonlinear equations that you had before. Clear? Any questions about this? This is the critical thing because we are going to make use of this in a big way later. Are there any questions? Am I connected? I think that should be an answer to that question.
Yes,
Yes,
sir, you're
sir.
connected.
Yeah, and there are no questions about this. All we are saying is that we can change my coordinate system to this new coordinates. The equation which a one-parameter subgroup obeys is simply this. And this basically is an equation for the coordinates themselves. This alpha function must obey alpha equals each alpha alpha. It should also obey alpha equals capital Xi alpha, right? Capital Xi alpha being nothing but the E. What you do is just move the H from here to here, and you get this equation. Okay? Now, why is this such a important thing? We actually said that we are going to try to reconstruct the group from the structure concepts, remember? That was what the aim was. Right, we will be given the group, given the structure concept, from that we will reconstruct the group, meaning we will find out the functions F ultimately. But as a stepping stone to that, we will find out the functions, etas and xis. And then from that move on to doing that. And I also said that that task cannot have a unique answer because you change your coordinate system, you can very well change your coordinate system in such a way that the CJKs don't change, the structure constants don't change, but the function f definitely does. So here what we are looking at, or we are going to try to do, is try to reconstruct the group, but uh, in this particular coordinate system using canonical coordinates of the first kind. So in addition to the equations that we have,
So we can't hear you.
I was just writing this down.
We couldn't even see you writing that. Yes.
Okay, can you see me writing that now?
Yes, sir.
So this was the equation that we had, right? We may minus C. Minus C, K, back now again, I guess. This and this are actually equivalent. In fact, two. Okay, let me also tell you your next assignment will be uploaded hopefully by this evening. And what I've done is this reconstruction thing is actually quite a lengthy calculation. So I'm really not going to do the reconstruction in the class because it's both going to be pretty boring for me as well as you to hear me keep on droning on and on about different. This up into many steps. Each of these steps should be simple enough, and put that as an assignment. So the assignment will be uploaded today. Half of half of the job of the reconstruction will be uploaded in this assignment, the next half in the next one. So you can realize that it's actually quite lengthy. So we have to sort of break it up into pieces. I'm not going to talk about the full reconstruction, all the steps in the reconstruction. I'm going to just show you how to do it. Each step should be easy enough. So later on, once you have submitted the tutor assignment, we can also discuss whether you did it right or not. And by the way, if you are stuck in any one step, so I've broken this up into many steps. If you are stuck in one step, you can just assume that the answer is right and go on and work out the next step. That is how the assignment is designed. So you should be able to at least each step. Okay, let me just show you roughly what it's going to look like. I don't know whether you can read this, but you can see my screen, right? See the assignment on the screen, right? So it essentially looks like this. Show that one equation. Then define an alpha dependent matrix, show that this equation essentially becomes this equation. Then show this. Then show the next step. Even if you cannot do one step, at least step you are supposed to, the next this one and the next one will actually do the rest of the not really worth it. Let me show you. Remember, we talked about this. So this is the equation. So this is the equation. Then show that this equation essentially becomes this equation. Then show the next step. Even if you cannot do one step, at least step you are supposed to do. So let me show you. Remember, we talked about. which we are and
Sir, are you speaking?
I did say we show. Can you hear me now?
Yes, now we can hear you.
Okay. I just hope the next class will be better with improved network. Um, now, as you move along, this again essentially tells you that if you move slightly uh, from the origin, where the alphas change slightly, how would a function on the group, on the manifold of the group, change by the application of this exchange? Now, what you can do is given a tangent vector, uh, confusing because we have already used it for other things. Let's say, what can we use? Let's do that anyway. It's standard. So we will say eta square bracket t is by definition minus tjxj. What does this mean? It should be pretty easy for you to figure out what this means. This essentially means that as you move along a one-parameter subgroup whose tangent at the origin is given by t, t1, t2, tr, this operator tells you how fast a function will change as you move along that particular curve. That is, this is minus tj now it's obvious that if you go down the commutator, you'll get this minus tjxj minus tkxk, sorry, ukxk. And using what we have just now, this will become 2 minus and make a plus, but the commutator itself here the minus. You get cljk tjuk xl, right? So this actually will be eta of another 10 vector v. And can you tell me what this v vector will be? What will the component of the v vector be? What in particular will VL be? Look at the definition. This is what eta t is. And we are getting this and we are calling this eta.
CLJK TJ UK.
Will be C the bracket of E and U. So if you have tangent vector with, so in other words, what we are saying is with this relation, this will be eta of t comma u, where t comma u is the vector v which has come later. It is also obvious that, well, you just look at this result. This
Sir,
Yeah.
You can understand that V is equal to third bracket T comma mu, U.
Well,
V is equal to,
yeah.
no, it's like
V is the
why are we
vector
saying
whose
this?
components are
V is
given by
equal to
this.
third bracket.
Hmm? Sorry. So what is your exact question? Is your question that you did not understand?
No, I mean we wrote NV, and then by using the definition we got VL.
All this vector V, the vector V,
Let's see your presentation
Sorry,
anymore.
we cannot see your presentation.
whose PH you switched off for some reason. This is something else. I'm just defining the bracket between two tangent vectors by saying the bracket between the two tangent vectors T and U is this vector V whose components are given by this. Okay?
So it's just a notation.
Yeah, it's just a notation or
Enough.
just a definition, as you can say.
Ah.
Okay? But this is real. So this bracket between, so this is the definition of the bracket between tangent vectors. This was a proper commutator. XJXK was a proper commutator. Okay, you actually use XJXK minus XKXJ, right? Okay, these are
Yes, yes.
differential operators. So XJXK minus XKXJ, that makes sense. You can actually think of what that actually is. And since these eta square bracket t's, these are also differential operators, which actually measure the rate at which functions change as we move along these one parameter subgroups. These brackets also make square bracket t. On the other hand, what do you mean by a commutator of two vectors? Am I still connected? Hello? It looks like I am still connected, but I can't hear anything from you.
Yes, sir, we can hear you.
Oh. Okay, so I was saying this is a proper commutator bracket, the way we have known from quantum mechanics or any other linear algebra scenario. But here we are saying that, okay, I'm describing a Lie bracket between define vector vectors in R-dimensional space. These are not dot products or cross products or anything. Yeah. So this is the definition. In fact, I will define form this VL by using the structure constant of the Lie group CLGKTJUK. Of course. Okay, I can. You still hear me, right?
Yes, sir.
So given two tangent vectors E and U with components T1, T2, TR, U1, U2, UR, I can form a vector V. Form just by using this. I will call this the Lie bracket of T and U. So here, remember, notice that I'm defining the Lie bracket using something else, which was a proper commutator. But this is not a commutator in any sense, right? Because commutator would mean you would multiply two things, then subtract by changing the order.
So
Here,
this thing is inspired from that XJXK bracket.
yeah, it is sort of something I'm trying to use the same properties which come from the XJXK bracket. But this is not the XGXK bracket. That is important to realize. Okay. It's not a commutator, but it's a bracket. I've defined a product of two vectors as well. But one important thing is, if I do this, first of all, this is basically what the bracket becomes, right? The commutator of two eta t eta u's is eta with the of the bracket of t here, right? If I take the lead bracket, this but now you are cyclic sum of this
Should be 0.
cyclic means, right? Because we know this is a standard commutator for commutator to do, right? But now one thing that you should also be able to see rather easily from the definition, eta t, the way we define eta t is just linear in the if then we have to use an tj plus tj by tj plus uj, that will automatically give you this. And what does that mean? That means that this cyclic of this bracket. This bracket is not the commutator bracket, but this will have to keep on obeying this property, right? If you take the cyclic sum of Tu with V, this also has. So what I'm trying to emphasize is, you started with a Lie bracket, with a commutator bracket between two operators. Which of course is not a commutator at all. But just like the commutator does, it also has to obey this identity, the so-called Jacobi identity. And the reason why I'm bringing this up is the following. We will next talk about this structure in the abstract. That is, a Lie algebra will be essentially defined to be a vector space, a bunch of vectors, which the set of all tangent vectors definitely is, on which a bracket is defined. So there should be some so-called product which acts on a pair of vectors to give you another vector, but that bracket will have to have these properties. Tu will have to be minus ut. That's one property. And the other property is this one. And the moment you have such a property, you call the thing a Lie algebra. This Lie algebra that we are talking about here was derived from a Lie group, but you can also think of a Lie algebra as an independent entity in its own right. A vector space, a bunch of vectors, on which, in addition to the standard properties of vectors, the standard addition of vectors, subtraction of vectors, and so on, you also have this additional property of a bracket defined. This gives us a Lie algebra whose properties we are going to explore in some detail in the next few classes. The reconstruction of the Lie group from the structure constants essentially is the reconstruction of the Lie group from the Lie algebra that we will do via assignments primarily, and maybe a tutorial once we have done the assignments. But the Lie group leads naturally. We have seen in general identity. Very often we don't even bother about the underlying Lie group. We look at the properties of the Lie algebra to really talk about most of the physical features from the Mac idea and everything. Okay, final thing. Any questions or comments? Okay, Mayank, I see that you're the only one left here. Can you hear me? Or are you just here because you've forgotten to switch off?